Okay, sorry guys, I got cut off there. So as the electrons pass from PQ to the cytochrome complex, hydrogens are pumped into the lumen. So we're going to have a buildup of hydrogen inside the thylakoid space here. They're going to go to PC over to photosystem 1, where they're going to get excited again, rise in energy, where they're going to get to FD, ferredoxin. Ferredoxin is going to then give it to our last electron acceptor, NAD plus reductase, and then it's going to turn into NADPH. This NADPH is a high electron carrying molecule that's going to go to the Calvin cycle. Okay. With this buildup of hydrogen ions, we are going to create an electrochemical gradient inside the thylakoid membrane. This electrochemical gradient is going to cause the pumping of hydrogen through this ATP synthase, and we're going to create ATP from that. So remember this membrane integrated protein here. It's ATP synthase, works the exact same way as the electron transport chain. Every time a hydrogen is pumped through it, down the concentration gradient, it's going to turn the turbine, and we're going to create ATP. So ATP is going to the Calvin cycle. NADPH is going to the Calvin cycle. Oxygen here. Oxygen is actually just going to diffuse right out of the cell and right out of the leaves into the atmosphere so that we can use it to breathe. So what I've done is I kind of this is right word for word. I just put it in the fill in the blank note. It's kind of what I want you. It's kind of what I want you to know. You can pause it. You can take a look at it. Same thing applies for this. I'm just gonna put up the steps that are taken in that diagram above individually. You can give it a read. You can pause it, you can read it, you can have a better understanding of what happens in each step. I'm just not going to go through because it's just too much. So pause it if you need to. Okay, so after we've gone through that linear cycle, that NADPH is going to provide the reducing power for the synthesis of sugar in the Calvin cycle, which we'll talk about next week. Okay, so right at the start, photosystem 2. That's kind of our first photosystem, even though it's called photosystem 2. Water split. Okay, photosystem 2 is a very strong oxidizing agent. It's going to pick up electrons. So once the water is split, the electrons from the water are going to get taken up by photosystem 2. And the water is just going to keep replenishing the electrons that go through this cycle. Okay. So the thylakoid proteins, we got ATP synthase. So protons are pumped into the lumen during the electron transport chain. So inside the lumen, we're going to have a big electrochemical gradient, and then they're going to be pumped down, producing ATP. And we call this photophosphorylation because we're just using photons to oxidatively phosphorylate ATP from this. So as the hydrogens come in, we create this electrochemical gradient for the ATP synthase to synthesize ATP. Okay, last thing here. There's two types of electron transport. There's non-cyclic and there's cyclic. So the non-cyclic is everything we've been talking about. It's the Z scheme. So there's no cycle here. Electrons get excited, move through electron transport chain, get excited, move through electron transport chain. There's no cycle here at all. Now, this is what it looks like. Ferredoxin, this FD here, this carrying protein, it can have two fates. One, it can be non-cyclic and it can continue this way, and it can give the electrons the NADP plus reductase, and then we can get NADPH. Okay? That's one thing that it can do. it can also come back and give those electrons to the cytochrome complex. And when it gives it to the cytochrome complex, that cytochrome complex is going to pump hydrogen ions into the lumen. And then it's going to go to PC, back to photosystem, and then it can go here, and it can get recycled. This is the cyclic portion, okay? This is the cyclic portion. So we can either create NADPH, or we can either produce hydrogen ions to get pumped into the lumen. And if we do that, then we're going to increase the production of ATP. Okay? So cyclic produces more ATP. Non-cyclic will produce ATP, but it'll also produce NADPH. Okay? Okay, so it only involves photosystem 1. We don't need photosystem 2 because photosystem 2 really only replenishes our electrons. We don't have to replenish it because it's a cycle, so they're going to keep cycling back and forth. So ferredoxin is going to return electrons back to the cytochrome complex. Those protons are going to get pumped into the lumen to produce more ATP through chemiosmosis, and no NADPH is going to be created. Okay, so if we look back at this, so instead of ferredoxin going to the NADP reductase, the ferredoxin is just going to come back here to the cytochrome complex. That cytochrome complex is pumping hydrogens. More hydrogens, more ATP produced. But what's the whole point of that? Why do we want to produce more ATP? It's simple. In the Calvin cycle, which we'll talk about next week, this is the whole fixing. This is fixing carbon and making glucose. This cycle needs more ATP than it does NADPH. So we need to figure out a way to make more ATP than we do NADPH. So by doing it the cyclic version, we're going to produce ATP without producing NADPH. So when ATP runs low, NADPH will accumulate because the Calvin cycle slows down. And when that happens, and when there's a rise in NADPH, it actually stimulates the shift to run the cyclic electron transport chain, or the cyclic flow instead of the linear flow. So that's it. This was a lot today, but this is going to be your note for Wednesday and Thursday. If you guys have any questions, message me on the Google Docs. I'll try to answer everything I can. Have a good day.